I said I would pick up here basically where I left off on Monday. So we're going to start with just translation. So this is covering the translation aspects, these two. Basically, well, and the basic translation is the first case, right? Any straight line, right? Straight line translation. So if the body is translated in a straight line, any particle obviously inside the body or on the body is also going to move in a straight line. So all the particles move in sort of parallel lines. And you can see this translation here is from A to B, right? And you can write position vectors like we've been writing before. And you can write the position vector B with respect to A. Yeah, so that's what this is, right? And then you can differentiate with time and get velocity, and then differentiate with respect to time again and get acceleration. And the only point here is this is just a proof to show you that yes, all the particles have the same velocity, all the particles have the same acceleration for straight line translational motion. Oh, I thought there was another. No, I guess that's it. So now we're going to talk about rotation. And rotation is always about some kind of fixed axis. And now that axis can be changing, and we're going to get into that. That's a more complex topic. But just look at the rigid body here rotating about, well, they labeled the axis A prime, right, which is the z-axis here. And it's rotating, looks like this way, right? So you can write a position vector for that point P, right, for any given point at any given position on this thing, and describe the rotation based on that position vector. So let's look at the velocity of the vector. The velocity vector is going to be that dr dt, right? That's the position vector, and it's going to be a change with the with time. And notice it's a tangent to this path. The velocity vector is tangent to this path. So whatever that path is, that's the or whatever this this circle is, that at whatever point you're at, your tangent, your velocity is tangent. So this is the magnitude ds dt. Let's see. This is just basically doing the math to get the velocity. ds dt is the limit, right? As your delta t approaches 0, right? So just an incremental position here of r sine phi, right? And phi, notice the phi in here, right? That's that phi, and that's d theta dt, right? So it moves, it's moving in a small increment theta in a certain amount of time. And you can do this, you can do the cross product and get, well, let's see, we get r theta dot sine phi for our velocity, right? So r theta dot, meaning the change in theta per, you know, d theta dt times sine of phi, which is just your angle here. And you can get the same result if you look at this thing for velocity, and you can do the cross product. So dr dt is just omega cross r, right? So omega is your rotational speed, basically, right? And that's how you get your velocity. And you wind up here with theta dot k, and that's your angular velocity. Oops. You would just cross these, right? You have to come up with an expression for r, and you have to know the value for omega. All right. Oh yeah, concept quiz. Let's see. Let's put the poll up here. How many people we got? Oh, we're up to 6. All right. What's the direction of the velocity of point A on the turbine blade? And they give you a few options. The direction of the velocity at point A. So this really should be kind of left over from you know, previous work as well. It's not just based on the new information you were given. Yeah, I was looking at the textbook the other day, and it's like, well, the slides are not, you know, they skip a lot of steps in the slide, and if you really, it's almost like if you really want the derivations for the more detailed pieces, you got to go into the textbook and follow the equations better. There's just not enough room on the slides. All right, what do we got? Five people out of 6. All right, most people in the poll. Most people got D. And what am I doing here? D is the answer. Yeah, the tip at that instant, right? The tip of the turbine, its velocity is pointed tangentially, right, to the path of rotation. So tangentially, that's the vector V. Close the poll. Oh, yeah, I forgot I wrote these equations here. Let me see, do I have one more? No, that's it. So VA is just omega, right? Cross product with R, the position vector. And that can be written as, in this case, omega K cross with negative Li, assuming you change your, you know, that's the coordinate system you choose, right? Yeah, so you wind up with VA is just negative L omega J, right? So that's the J direct, negative J direction. And you can see the coordinate system is written like that. All right. Let's look again at rotation about a fixed axis. Here it shows you the formula for acceleration. And it shows you how you can get that by just differentiating the dv dt equation, right? So we have the derivative of omega cross R. And of course you do your distributive, what is that called? Chain rule for taking derivatives. And you wind up with this, this format for the acceleration, right? Again, notice 2 terms. We got a d omega dt. Let's see. We got an omega cross V. And you can notice here that d omega dt is angular acceleration, right? This is angular velocity. This is angular acceleration. So we can replace that with angular acceleration. And we can also see that angular acceleration is equal to any of these terms, right? It's omega dot. It's also theta dot. Or sorry, double dot, theta double dot. Yeah, so it's basically a vector combination, right? It's 2 vectors. You've got your acceleration cross R, right? Plus your omega cross R. And these are the tangential acceleration components and the radial acceleration components, right? The normal acceleration. Remember that term from before, except it looks a little different with the cross products. Let's look at a very simple example. You've got this slab. It's like a large chunk of rock moving in space, and it's in motion here. And notice the let me go to the next bullet here. Well, yeah. Notice the coordinate system they drew, right? You can draw for a given point P, right? You can draw that position vector. And you've got omega is omega K, right? That's the angular velocity of this thing. And then for a given point at a given instant, the velocity is just omega K cross R. So we just get R omega for this velocity. Now you look at acceleration. We've got, let's look at this term, right? We've got AK cross R, right? Cross R. And then we have omega cross R. And you wind up with wind up with these terms down here, AK cross R minus omega squared R. And so you wind up with a few different components to look at. We've got our tangential component is AK cross R, right? So AK cross with R, and that just turns out to be R alpha. Oh, I'm sorry. This I should specify alpha. Alpha is the angular acceleration. Sorry about that. They look too look too close on the slide. This is A. This is alpha, right? This is your acceleration vector. This is your angular acceleration. So the alpha is your angular acceleration, and then your normal acceleration is just your angular velocity times the vector squared. One other thing here, once you take the vector out, right, you realize the direction. This is the magnitude of it. Those two values right there. Right. What's the direction of the normal acceleration of point A on the turbine blade? Let me see if my poll is. So we've got normal acceleration of a point A on the turbine blade, normal acceleration. Go ahead and put a guess up there. Oops. All right. It's like a bunch of people said B, a bunch of people said D. Yeah, A is the answer. So remember, normal acceleration is points inward towards the direction of towards the point about which you're rotating. And then this is the one that confuses people, because we always think about, when we're driving, say like you're driving in a car and taking a curve, right? Or you're spinning around on one of those whatever ride spins around at the, at the park, right? You get some of those. What is the one where you stand up against the wall and that spins you around real fast, and you feel like you're being pushed outwards, right? But the acceleration, the normal acceleration, is defined as in towards the center, right? Because what's happening, this is keeping that point in position, right? So it's directed, the acceleration is directed inward. Yeah, so the normal acceleration is a negative omega squared R bar, right? R is a negative Li. So you wind up with a L omega squared I is your acceleration. Let me get this off the screen here. Oops. We're going to look at rotation of a rigid body again here. You can specify it again with angular acceleration, or the type of angular acceleration. So this is just, you're looking at some of the stuff we've learned before. Angular velocity d theta dt. You can rearrange this, right? dt is d theta omega. So you can rewrite angular acceleration as this quantity omega d omega d theta. And for uniform rotation, right, where angular acceleration is 0, right, you can just basically write this term, which is just the integration of, or rearrangement and integration of these of this statement up above, right? So you wind up with theta is theta naught plus omega t, and that should look pretty familiar to you. You can write these terms for this is basically like looking at your your rectangular coordinate acceleration and velocity equations, right? This is where they come from. So these, again, these apply for constant or uniformly accelerated rotation, right? So where alpha is constant. So you've got omega plus omega naught plus alpha t, right? This gives you whatever omega is. You've got your theta term, right? The initial theta plus your omega t plus 1/2 at squared. Again, very familiar, right? These are just like the rectilinear ones for velocity and acceleration in time and position. Same thing, omega squared is omega naught squared plus 2 alpha theta minus theta naught. So we can use those equations if we're given enough information and we're told that we have uniformly accelerated rotation. All right, these slides are left in from when I had this thing electronically last spring. I was only doing segments at a time for videos. Okay, so what do we got here? We've got this this fancy little wheel setup. We've got a weight, right, and it's attached to this wheel. And then in the center of the wheel, we've got this this smaller gear, and it's got attached to C. So this cable C has an initial acceleration of 9 inches per second squared and an initial velocity of 12 inches per second, both directed to the right. Determine A, the number of revolutions of the pulley in 2 seconds, and B, the velocity and change in position of the load B after 2 seconds. And then they also want to know the acceleration of point D on the rim of the inner pulley at time equals 0. So this is, again, some of this stuff is a rehash of old principles, but just now that we're in a rotational frame of reference, it makes it a little different and a little trickier to deal with. All right, so the first observation we can make is you've got this cable, and it's we're assuming there's pretty much no slip in this attachment of the cable to the center of the whatever it is, the center shaft, center pulley. What are they calling this? The inner pulley. So the initial assumption you can make is that the tangential velocity and acceleration of D is equal to the velocity and acceleration of C, right? Because this is basically the tangential vector of that point, right? So then from there, we're going to calculate the initial angular velocity and acceleration. So that's, oh, and then we're going to apply all the relations we just looked at to determine velocity and angular position. And then we'll look at the initial tangential and normal acceleration components of D. So there'll be components of D that we'll break down. All right. Oh, I'm going to shut that blind here. So nice and sunny yesterday. I have the blind. Just in the middle. Just focus that. It seems a little out of focus. I don't know why. All right. I'm just going to draw this out for a minute, this inner pulley here. Notice we're given radii, right? 3 inches and 5 inches, and we'll use those at some point. And there is this cable around it. Oops, I don't know why I did that. That's just the direction. And then we've got the center point. We've got D. Where's my red pen? This is 3 inches. And I'll draw the arrow here. This is omega. It's your angular velocity. Let's see, did I get that in? Yeah, the tangential, let's see, acceleration of point D. Let me put in here tangential. So the initial tangential velocity, d naught, is equal to the initial tangential velocity, c naught, right? And that's going to equal 12 inches per second. We're also given, let's see, acceleration, constant acceleration of 9 inches per second squared, right? So what we see here is the acceleration of c is equal to 9 inches per second squared. This is also equal to the tangential acceleration of d initially, right? Because again, they're basically connected. We're given the distance AD. Oh, I should label A in here. AD is 3 inches. So now what we're going to do is we're going to just use some of the equations we have. V d naught, right, is just r, the radius, times omega. And we have the angular, let's see, we're going to find omega. Oops. This is going to give us, I should put omega naught here. This is the initial velocity, right? So we've got omega naught is equal to v d naught over r. This is a d. This gives us 4 radians per second. We need a direction on this. Again, this is just taking your, this is kind of working backwards, right? You've got your tangential velocity, and we're trying to find omega. 4 radians per second. Well, this is going to be in the clockwise direction, right? We're still trying to, we want to figure out the number of revolutions of the pulley in 2 seconds. So we got to come up with some, let me just go back here to the slides for a minute. We've got to come up with some values of these components here if we want to use these equations. Let's see. We're going to wind up using, for uniform acceleration, right? We can use this equation to figure out what our angular velocity is going to be after a certain amount of time, given the initial angular velocity, right? And then we can also figure out theta here from the acceleration and the time. So we'll use all this stuff to figure out what the velocity and the angular acceleration are, and then we can figure out the number of revolutions at 2 seconds. So let's go back to the slide here. So that's our omega naught. Alpha, or acceleration. We know acceleration of g naught is r alpha, right? We know r, we know the acceleration, initial acceleration, we got that up here, right? 9 inches squared per second, or 9 inches per second squared. We can rearrange this and find alpha. This is ADT. And remember, alpha is going to be constant acceleration of 9 inches per second squared over a 3-inch radius. And this is 3 radians per second squared. And the acceleration for this one, again, is also clockwise, right? We're accelerating in, well, our component of acceleration is, our rotation is clockwise in this case. Now we have the equations for uniform acceleration. For uniform acceleration, I'm going to write this. Let's see. Yeah, I'll just start with the first equation. Omega equal to omega naught plus alpha t, right? So here we have omega naught, the initial angular velocity is 4 radians per second. Let's find at time equals 2 seconds. So I'm going to basically be putting 2 seconds into these equations here to figure out what the angular acceleration or angular velocity is, and then we'll also figure out theta. Because we're asked for velocity and change in position after 2 seconds. Oh yeah, velocity and change in position of the load after 2 seconds, plus the number of revolutions in 2 seconds. Maybe I should have done theta first. All right, well, we're already here. So let's see, we got 3 radians per second squared times 2 seconds. This just gives us 10 radians per second clockwise. This is omega, right? We'll call this omega 2 seconds, I guess. Theta at 2 seconds, I'll put a little 2 here. It's equal to theta naught plus omega naught t. This is right out of the, again, the set of equations we just looked at. Angular acceleration, t squared. Yeah, I got to be careful with a and alpha. This first component here, theta naught, is 0, right? Initial theta, you can just pick arbitrarily. We're picking our initial theta is starting like this, right? That's just 0. We want to know after 2 seconds, how many or how much theta have we rotated? And this is going to be in radians. And then from that, we can get the number of revolutions. So I'm going to have omega naught t. Omega naught is up here, 4 radians per second. Times the time of 2 seconds. Plus 1/2. And then we've got alpha is 3 radians per second squared. Times 2 seconds squared. This is going to give us, let's see, we got 6, 4, 2 times 3, 6. Yeah, so 8 plus 6, 14 radians. So to get the number of revolutions, right, we just take the 14 radians and we multiply 1 rev is 2 pi radians. I mean, you could do half, as it doesn't matter, it's the same formula. Here you're going to get 2.23 revolutions. Yeah, I keep forgetting I meant to put this in the after the theta, because you really didn't need omega 2 for this this calculation. So for part B now, we do need omega information. Part B, the velocity and change in position of the load B after 2 seconds. So the velocity, oh, you know what? Let me draw this out here. Now we're not given a letter, but I'm going to put one in here. This is B. And over here, tangential to where this rope or cord makes contact is E. We'll call that E. And we've got a center point. We have omega. And we have a radius of 5 inches. So this is what we're looking at for weight B. So it wants us to know the velocity and change in position of the load after 2 seconds. So the angular velocity, right, it doesn't matter if it's on this small 3-inch pulley or this 5-inch pulley. The angular velocity is the same. What we need to figure out is what's the velocity, basically the tangential velocity. And we can figure that out by knowing that, all right, VB, the velocity of B, is going to be equal to the velocity at E, right? Because E is where the cord is making contact tangentially to the pulley. And that's just going to be R times omega. And we're going to write it 2 seconds here. Yeah, so I'm going to use 5 inches. And my angular velocity at 2 seconds was 10 radians per second. So this gives me 50 inches per second. And the velocity is directed upward, right? That's the direction, 50 inches per second up, right? B is always going to be moving, well, at least until it hits the pulley, it's going to be moving up at 50 inches per second. And then it says, let's see, velocity, acceleration, change in position of the load after 2 seconds. So the change in position of the load after 2 seconds. Well, let's see here. We've got, we don't even have to worry about angular velocity for this one, right? We just need to know that after 2 seconds, it's already rotated 2.23 revolutions. So we just got to figure that out, what that is in terms of length, right? And you can see that the delta YB is just going to be equal to R times theta, right? So R times theta, right, gives you, if theta is 2 pi, right, that is the circumference of the circle, right? 2 pi r. Pi times diameter, that's the circumference. So we're basically translating we're getting a linear displacement by knowing that this point, right, moves around a circle. And we're just taking basically the equation for arc of a circle, right? So we have here, we have R is, in this case, 5 inches. And then theta is up here, 14 radians. Don't forget, you can't just use revolutions. Yeah, revolutions. You'd have to convert revolutions into, you'd have to use your pi to convert into radians. That's where the equation for the circumference of a circle comes from, right? 2 pi r, or pi times diameter. So here we have 70 inches. So I'll just write it, I'll summarize here. VB is 50 inches per second upward, and delta Y of B is 70 inches up. The last part here, are there any questions so far? Let me go back up here. Acceleration of the point D on the rim of the inner pulley at time equals 0. We did that, but we want to know the, where are the velocity change? Oh, we're supposed to get the vectors. I didn't actually write that. Let me see the velocity, acceleration. Yeah, we're going to get the vectors here. So we're going to break down the vectors. Let me just do it like this for a minute. So part C, acceleration of D has both normal and tangential components. In terms of the tangential components, come on, there we are. We already figured that out, right? R times angular acceleration. I'm going to rewrite that. But then for the normal component, we're going to use this equation, R omega squared. So let's go back here. This is just the acceleration of C, and we figured that out. This is 9 inches per second squared. I'll just put from part A. Right, so part A was this. We already used that relationship. For part D, or for part D, for the normal component is going to be R omega naught squared. All right, we're looking for the initial acceleration. So we've got 3 inches times 4 radians per second squared. And that's just going to be 48 inches per second squared, right? So now we're actually converting this to a time, or sorry, a distance measurement. So now what I want to show here is I'm going to draw some sketches here so we can see how everything's going. My wheel, I've got, I'll just draw it in blue. So I don't know what happened to my pen. This is point D. Oh, point A is in the middle. Now, here we have 2 components. We've got AN, and we've got AT. Remember, the normal component is always facing in towards the center of rotation. And I've got my tangential component. So we have a vector system, right? And we've got A, the normal is 48 inches per second squared down, right? So all we're doing here is we can come up with a vector triangle. I'll rewrite this so we can see things. Got 9 inches per second squared. We can use the parallelogram rule too, right? Up there. Oh, I need an angle. Let's call this angle, I don't know, phi. Just to differentiate it from theta, which is angular, or theta is around in this direction here. All right, so now we find that A of D is just 9 squared plus 48 squared. This gives us 48.8 inches per second squared. This is our acceleration, and our phi is just the inverse tangent. So this phi here is the inverse tangent of 48 over 9. Did I number right? Let's see. Yeah, looks like I did. This is 79.4 degrees. So at time equals 0, the acceleration of D is 48.8 inches per second squared at an angle of 79.4 degrees. So notice my reference, right? My reference axis for the angle. So that's how you do these problems in sort of rotational coordinates, right? Remember, again, as we learned earlier, acceleration is pointed towards the center, and obviously tangential is outwards like that. Yeah, so that's example 1. Are there any questions about example 1? Oh, 45. Let's see. What's after this? Don't think I go to another example. Oh, general plane motion. Let me just really quick talk about general plane motion. Well, a little bit about it. I'm not going to get through all these slides, but this is a planetary gear system, and this is interesting because they can transfer high torque to load or weight ratios in this case, and they're used to basically reduce. You can get high reduction ratios here with these planetary gears. But what happens, right? The center of the gear is translating while the gear rotates about its center, right? So this everything's in motion, right? But this is rotated on the inside. And when you deal with general plane motion, what we've got here is we've got neither pure translation nor pure rotation, right? So look at this. This circle moving, right? It's like a bicycle wheel. So a lot of common applications in just point A and B start off like this. As it rotates, right, point B changes position. Point A pretty much stays in the same spot. Now, we can look at this as a superposition of two motions. We can look at this thing as this whole circle has been translated, right? That's a direct translation with A. Plus, it's been rotated about A to get B's new position, right? So it's like instead of looking at this as a rotation that moves over to this point, you look at it as I'm translating it and then I'm rotating it without moving it obviously along the plane, or I'm rotating it and then I'm translating it, right? So you can look at it as a combination of those two events. And it's basically the sum of those, right? So here's let's see, particle A and particle B. Notice this object, right, can be written as, see how it moves? It moves over like this. It can be written as a translation from A1 to A2, and then a rotation of B1 prime about A2, right? So the whole thing is translated. You get a new position, A2, B1 prime, and then you rotate it to get B2. So we're going to be dealing with problems where we can look at plane motion. We can break it down into a translation component and a rotation component. And picking those points of rotation is obviously important. But let's pick up here next time on Wednesday. All right. So everyone have a good morning, and I'll see you all in mechanics this afternoon.
All right.